China's Bamboo Revolution, the controversial high-speed train that shocked Japan. When you picture bamboo, what comes to mind? Perhaps elegant garden fences, traditional Asian architecture, or artisanal crafts passed down through generations. For thousands of years, this resilient plant has served humanity in these familiar ways. But what if I told you that bamboo is now at the cutting edge of transportation technology, competing with steel in one of the most demanding engineering challenges of our time? Welcome to the story of China's bamboo train, a technological breakthrough that's rewriting the rules of modern rail transport and leaving even the world's railway pioneers questioning everything they thought they knew about high-speed travel. Before we dive into this remarkable journey, if you're fascinated by stories of innovation, breakthrough technology, and how nations are reshaping our future, make sure to subscribe. Hit that notification bell so you never miss our deep dives into the stories changing our world. Now let's explore how a plant that grows in forests became the centerpiece of a transportation revolution, from ancient material to future technology. The 21st century has brought us countless innovations, but few are as surprising as China's decision to reimagine one of humanity's oldest materials. While most nations focused on advanced alloys, carbon nanotubes, and synthetic polymers, Chinese researchers looked in an unexpected direction toward the bamboo groves that have dotted Asia's landscape for millennia. This wasn't a romantic return to tradition. It was a calculated scientific gambit based on years of materials research. Beginning in the early 2010s, Chinese materials scientists embarked on an ambitious mission. Could they transform bamboo into a viable alternative for manufacturing high-speed rail components? The hypothesis seemed almost absurd. After all, we're talking about replacing hardened steel, the backbone of industrial civilization, with what is essentially a grass. But these researchers understood something that hadn't been fully appreciated. Bamboo possesses a unique cellular structure that gives it remarkable mechanical properties, combining flexibility with surprising strength. After more than 3 years of intensive research and development, involving countless failed prototypes and setbacks, the breakthrough finally arrived. Chinese scientists successfully engineered what they called bamboo winding composite material, a revolutionary substance that could withstand the extreme stresses of high-speed rail operation. The first test runs were nothing short of extraordinary. Trains incorporating this bamboo-based technology exceeded speeds of 100 kilometers per hour, demonstrating that this natural material could indeed perform in one of engineering's most demanding environments. When news of this achievement spread internationally, the reaction was immediate and polarized. The global engineering community found itself divided. This was particularly true in Japan, a nation that had pioneered high-speed rail technology with its iconic Shinkansen bullet trains decades earlier. The Skeptics Speak Out. Japanese railway engineers, drawing on over half a century of high-speed rail expertise, raised substantial concerns. Their skepticism wasn't rooted in bias. It came from hard-earned experience and rigorous safety standards that had kept millions of passengers safe across billions of journeys. The traditional approach to high-speed rail construction has always centered on steel. This material has proven itself across every conceivable condition: extreme temperatures, massive impacts, metal fatigue over millions of operational cycles, and the constant vibration that comes with trains moving at hundreds of kilometers per hour. Steel isn't just strong, it's predictable. Engineers know exactly how it will behave under stress. Decades of real-world data inform every decision, every safety calculation, every emergency protocol. When you board a high-speed train, that confidence in steel is part of what keeps you safe. So, when China announced bamboo trains, the immediate question from critics was simple. Can a plant-based material really match the proven reliability of steel? Can it protect passengers during a collision? Will it maintain structural integrity over years of constant use? These weren't just technical questions. They touched on something deeper, the fundamental question of whether we should trust ancient natural materials in ultra-modern applications, or whether some innovations simply push too far beyond proven boundaries. But to understand why China pursued this unconventional path, we need to look at the economic realities driving innovation in the world's largest high-speed rail network. The economic pressure behind innovation. 3 decades ago, China's transportation infrastructure told a story of a developing nation struggling to modernize. Railways were slow, road networks were inadequate, and the country lagged far behind Western nations and Japan in transportation technology. Fast forward to today, and the transformation is staggering. By 2023, China had constructed over 45,000 kilometers of high-speed rail lines. A network so vast it represents more than 3/4 of all high-speed rail track on Earth. No nation in history has built transportation infrastructure on this scale, at this speed. China now operates the most extensive and technologically advanced railway system the world has ever seen. Trains routinely cruise at 350 kilometers per hour, connecting cities across a continent-sized nation. The network has fundamentally transformed how over 1 billion people live, work, and travel. But beneath these impressive statistics lies a troubling financial reality that most people never hear about. Despite its technical success and massive popularity, China's high-speed rail system operates at a substantial loss. The accumulated debt from building and operating this network has surpassed $830 billion, a figure so enormous it's difficult to comprehend. Why is a system this successful losing so much money? The answer lies in the brutal economics of high-speed rail construction and operation. Consider the costs involved. A single standard high-speed train costs approximately $17.9 million to manufacture. Each individual carriage within that train represents an investment of about $2.2 million. And that's just for the basic models. The more advanced electric multiple units, the premium trains offering enhanced comfort and performance, carry even steeper price tags. These can cost upwards of $30 million per complete train set, with each carriage running around $2.7 million. Now multiply those figures by the scale of China's needs. Over the past 5 years, the country has manufactured more than 1,200 new trains annually just to maintain and expand its network. The cumulative cost is astronomical. The materials driving these costs are familiar to anyone who knows manufacturing specialized metals, advanced carbon fiber composites, and proprietary alloys engineered for specific performance characteristics. These materials deliver excellent performance, but they come with 2 significant downsides. First, they're expensive. The global supply chains for aerospace-grade metals and advanced composites involve complex processing, limited suppliers, and high market prices. Second, they're environmentally costly. Producing steel requires massive amounts of energy, generates substantial carbon emissions, and consumes finite resources. Carbon fiber production, while creating lighter materials, involves energy-intensive chemical processes. China found itself at a crossroads. The nation needed to continue expanding its rail network to serve its population and drive economic growth. But the financial and environmental costs of traditional materials were becoming unsustainable. This pressure created the perfect conditions for radical innovation. If Chinese engineers could find an alternative material that was cheaper, more sustainable, and still safe and reliable, it could transform the economics of high-speed rail, not just for China, but potentially for developing nations worldwide. The search for that alternative led researchers to examine materials that were abundant, renewable, and native to China's landscape. And that's when bamboo entered the conversation. The bamboo advantage. Why this plant makes sense. To understand why bamboo emerged as a serious candidate, we need to appreciate just how remarkable this plant really is. Bamboo is one of nature's most impressive structural materials. Unlike typical wood, which has a relatively uniform cellular structure, bamboo evolved as a hollow cylinder reinforced by nodes. natural engineering that creates exceptional strength-to-weight ratios. When you examine bamboo under a microscope, you see long, parallel fibers running through its structure. These fibers give bamboo extraordinary tensile strength, the ability to resist being pulled apart. In some species, this tensile strength approaches that of steel. But bamboo offers something steel cannot: flexibility. While steel is rigid and can become brittle under certain conditions, bamboo bends without breaking. This elasticity means it can absorb impacts and vibrations, returning to its original shape after stress is removed. Chinese researchers recognize that these properties, strength, flexibility, and resilience, made bamboo an intriguing starting point for developing composite materials. The engineering challenge was clear: take bamboo fibers and combine them with other materials to create a composite that could match or exceed traditional materials in specific applications. The solution they developed was elegant. By extracting and processing bamboo fibers, then combining them with resin binders in a carefully controlled winding process, they created what they termed bamboo winding composite material. The concept behind composite materials is well established in engineering. You combine materials with complementary properties, for instance strong fibers embedded in a binding matrix, to create something that performs better than either material alone. Fiberglass and carbon fiber composites work on this same principle. What made the bamboo version special was its raw material source. The researchers found that properly processed bamboo fibers could serve the same structural role as glass or carbon fibers, but with distinct advantages. Testing revealed impressive results. The bamboo composite material achieved compressive strength comparable to C30 grade concrete, a standard used in structural construction. Despite being significantly lighter than steel, it could bear enormous loads without failing. But the real advantages went beyond pure performance metrics. The sustainability revolution. Consider the resource implications. Steel, like petroleum and coal, comes from finite geological deposits. We extract iron ore, process it at tremendous environmental cost, and eventually those deposits will diminish. Bamboo represents the opposite paradigm. It's one of the fastest growing plants on Earth. Some species can grow nearly a meter in a single day. A bamboo grove reaches full maturity and can be harvested in just 3 to 5 years, compared to decades for traditional timber. This rapid growth makes bamboo a genuinely renewable resource. Harvest a bamboo forest responsibly, and it regenerates quickly without replanting. The same grove can be harvested repeatedly for generations. The environmental accounting is striking. Producing steel requires mining operations, blast furnaces operating at extreme temperatures, and intensive energy consumption. The process releases substantial carbon dioxide and other pollutants. Bamboo processing, by contrast, is far gentler. While creating bamboo composites still requires energy and chemical binders, the overall environmental footprint is dramatically smaller. There's another consideration that's often overlooked: end-of-life disposal. When a steel train carriage reaches the end of its service life, typically after decades of use, it must be dismantled and recycled or scrapped. While steel is recyclable, the process still consumes energy. Bamboo composites offer potentially simpler disposal pathways. The organic component can potentially biodegrade or be converted to other uses with less environmental impact. The economics of bamboo. The cost advantages become apparent when you run the numbers. To produce a given volume of bamboo composite material, you need far less raw feedstock than producing equivalent steel. Let's look at a specific example. Manufacturing 10 million tons of bamboo winding composite pipes requires approximately 25 million tons of raw bamboo. That might sound like a lot, but compare it to steel production. Creating steel pipes of the same weight demands about 45 million tons of crude steel, which in turn requires roughly 22.8 million tons of coal for processing. The resource consumption is nearly double, and that's before considering the additional industrial infrastructure needed. For China, with its extensive bamboo forests and agricultural capacity, this represents a strategic advantage. The country can source bamboo domestically, reducing dependence on international metals, markets, and foreign suppliers. When you're building trains by the thousands, these cost differences compound dramatically. Reducing the material cost of each carriage by even a modest percentage translates to hundreds of millions of dollars in savings across an entire production run. This economic logic made the bamboo train program not just an environmental initiative, but a hard-headed business decision. If China could maintain safety and performance while reducing costs, it would gain a significant competitive advantage in global rail technology. But that crucial if brings us back to the central controversy. Can bamboo really be safe? Proving safety, the rigorous testing regime. When Japanese engineers expressed their doubts, they were asking the right questions. Safety in transportation isn't theoretical. It's measured in lives protected or lost. Chinese researchers understood that no amount of environmental benefits or cost savings would matter if the material failed during actual operation. The bamboo composite would need to prove itself through the most rigorous testing imaginable. The testing program they designed was comprehensive and honestly, pretty unforgiving. They subjected bamboo composite materials to stress tests that would destroy lesser materials. One of the most dramatic tests involved placing bamboo composite structures under an 80-ton truck and applying full crushing pressure. The material had to bear this enormous weight without catastrophic failure. When tested, the bamboo composites passed. They held the load without collapsing. But supporting static weight is only one challenge. Railway materials must also endure constant stress over years of operation. To simulate this, researchers conducted 10,000-hour continuous pressure tests, monitored by China's Building Materials Testing Center. These marathon tests revealed something remarkable. The bamboo composites showed exceptional fatigue resistance. While many metals can become brittle or develop microfractures after repeated stress cycles, the bamboo material maintained its structural integrity. The natural resilience of bamboo fibers contributed to another crucial safety feature: impact absorption. When a train encounters sudden forces, whether from track irregularities, braking, or collisions, materials that can absorb and dissipate energy protect passengers better than rigid materials that transfer shock. Testing showed that bamboo composites exhibited superior vibration damping compared to traditional materials. This meant not just better passenger comfort, but potentially improved safety during accidents. From laboratory to railway. The first bamboo trains. Satisfied with laboratory results, Chinese engineers moved to the next phase, building actual trains. In 2017, a major Chinese railway company committed $300 million to develop a fleet of trains incorporating bamboo fiber technology. This wasn't a small pilot program. They planned to build 12 complete trains, demonstrating confidence in the technology's commercial viability. The project moved quickly. By 2018, in the city of Hohhot, located in China's Inner Mongolia Autonomous Region, the world's first high-speed train using bamboo winding composite materials rolled off the production line. This wasn't just a prototype or a concept vehicle. It was a fully operational train, built to commercial standards and designed to carry passengers. The comprehensive testing program that followed examined every aspect of performance. Engineers measured compression resistance, earthquake and vibration tolerance, acceleration capabilities, and maximum safe speed. The results exceeded expectations in several areas. The compression resistance of the bamboo composite components surpassed traditional steel equivalents. This meant the structure could handle greater loads without deformation. Vibration and shock resistance tests also showed impressive performance, confirming that the material's natural flexibility translated to real-world safety benefits. The speed trials demonstrated that the train could safely achieve and maintain 100 kilometers per hour, a significant milestone proving that bamboo composites could function in actual high-speed rail applications. This successful demonstration sent a clear message to the international engineering community. Bamboo trains weren't science fiction or experimental curiosities. They were real, functional, and potentially transformative. The speed question, looking ahead. Of course, 100 kilometers per hour, while impressive for a first-generation bamboo train, falls well short of China's current high-speed rail capabilities. The country's advanced trains routinely operate at 350 kilometers per hour, more than 3 times faster. Some critics pointed to this gap as evidence that bamboo trains were interesting novelties, but not serious alternatives to conventional technology. This perspective misses the broader context. First-generation technologies rarely match the capabilities of mature systems that have benefited from decades of refinement. When Japan launched its first Shinkansen in 1964, the maximum speed was 210 kilometers per hour. Impressive for the time, but far below what modern trains achieve. That initial achievement laid the groundwork for continuous improvement. The bamboo train program should be understood in similar terms. The 100 km/h demonstration proved the fundamental concept. It showed that bamboo composites could function in rail applications and meet basic safety requirements. The question isn't whether first-generation bamboo trains match current conventional trains. The question is whether the technology can improve, and whether future generations of bamboo composites might eventually match or even exceed the performance of traditional materials. Chinese researchers are continuing to refine the bamboo composite formulations, experimenting with different fiber preparations, resin systems, and manufacturing processes. Each iteration aims to improve strength, reduce weight, and enhance performance. There's also the question of optimal applications. Perhaps bamboo composites won't replace steel in ultra-high-speed intercity trains operating at maximum performance, but they might be ideal for regional rail networks, urban metro systems, or developing nations building transportation infrastructure on limited budgets. The development of viable bamboo train technology has implications that extend far beyond China's borders. Consider developing nations in Asia, Africa, and Latin America. Many of these countries desperately need improved rail infrastructure to drive economic development, but they face the same challenge. Conventional high-speed rail is extraordinarily expensive. If bamboo composites can reduce costs significantly while maintaining acceptable safety and performance, they could make rail development feasible for countries that currently cannot afford it. Bamboo grows extensively throughout tropical and subtropical regions. Countries like India, Indonesia, Vietnam, Brazil, and many nations in East Africa have substantial bamboo resources. For them, bamboo rail technology could be transformative, allowing them to build modern transportation networks using locally sourced, sustainable materials. This technology could also influence the broader materials science field. If bamboo composites can work in demanding rail applications, where else might they be useful? Could they find applications in automotive manufacturing, aerospace, construction, or marine engineering? The bamboo train program demonstrates a broader principle. Sometimes breakthrough innovations come not from inventing entirely new materials, but from reimagining ancient ones through modern engineering. As global climate concerns intensify, the environmental advantages of bamboo technology become increasingly relevant. Transportation is one of the largest contributors to global carbon emissions. While electric trains are far cleaner than cars or planes, the manufacturing process for trains still carries substantial environmental costs. If bamboo composites can reduce the carbon footprint of train manufacturing by even a modest percentage, the cumulative impact across thousands of trains would be significant. There's also the broader circular economy consideration. Our current manufacturing paradigm relies heavily on extracting finite resources, using them once, and then dealing with waste disposal. Materials like bamboo that can be sustainably harvested, used, and then returned to natural cycles represent a different model. one that could become increasingly important as resource constraints tighten. Despite the promise, significant challenges remain before bamboo trains become commonplace. Long-term durability in varied climates remains unproven. While testing has been extensive, nothing replaces decades of real-world operation. How will bamboo composites perform after 20 years in tropical humidity? In desert heat? In freezing Arctic conditions? Maintenance protocols need development. Technicians working on trains need clear guidelines for inspecting bamboo components, identifying damage, and making repairs. These protocols don't yet exist with the same detail as those for steel trains. Manufacturing scale presents another hurdle. Building a few dozen trains with bamboo composites is one thing. Producing thousands annually requires industrial processes, quality control systems, and supply chains that don't currently exist at that scale. There are also regulatory considerations. International railway safety standards were developed around traditional materials. Gaining certification for bamboo trains in markets outside China will require extensive documentation, testing, and likely negotiation with regulatory bodies. Perhaps the most important aspect of China's bamboo train program isn't the specific technology, but what it represents about innovation itself. For decades, the conventional wisdom in railway engineering was clear. Steel is the only viable material for high-speed trains. This assumption was so deeply embedded that few engineers even questioned it. Chinese researchers questioned it anyway.